time for us to do some problems with optimization, or some people might say, the best of calculus. As always, it's important that you do the practice. In this part of the class, it's really a lot about translation. We're translating from the language that we normally use into mathematics. And as with any language translation, it's not so easy. There's subtleties, there's things you have to pick up on, little clues and context. And so that practice will help you learn to translate into math a lot better. Now, as you're doing the videos, if you haven't finished the problems yet, make frequent use of that pause button and pause and see where you can get by yourself. And if you need me, go ahead and unpause, and I'm there to help you along. All right, well, I hope we enjoy these problems. Let's begin. Our first problem. Find the maximum area we can enclose using 400 feet of fencing in the shape of a rectangle where one side does not need any fence. For example, it might be built next to a river or a cliff or other object which can act as a natural barrier. All right, now one of the things we should of course learn is how do we recognize optimization problems. They're usually pretty easy. When it says things like find the maximum, that's an optimization type problem. Whenever we're looking for a maximum or a minimum, that says we're trying to find an optimal value. All right, well, let's think about our setup. So we're going to build a fence where we really have three sides of the fence. There's a fourth side we don't need. So we can say, well, here we go. We'll draw ourselves a picture. Here's a river. Now you might say, how do I know it's a river? Well, clearly it's a river because it says it right there. All right, now what do we have? Well, we're going to have our rectangle. So it's going to look something like this. Now, it's probably going to be the case that it's a little bit longer than it is taller. You can imagine I could have 400 feet. And of course, I could do something really ridiculous, like build it way, way, way out, very thin, and way, way back. Yeah, that's possible to build, but it isn't efficient to build. So logically, we feel like it should be more closer to this shape than that shape. Well, let's see what the math says. Now, whenever we have a rectangle, of course, we have multiple sides. And so let's label our sides. We'll label this side, we can call it Y, and this side, we can call it X. Now, what is it we're trying to optimize? Well, we're trying to find the maximum area. So this is what we're trying to optimize. So our goal is optimize area. Well, let's think about what our variables say. So our area, it's the area of a rectangle, you take, length and width multiplied together. So it's X times Y. Are we ready to do our calculus yet? Not yet. Our problem is we have two variables here, X and Y. But X and Y are not independent. There's a relationship. And of course, we strongly suspect that there should be a relationship using the 400. Anytime we see a number, it's like, hey, there's probably a math reason that it's there. So oftentimes when we're scanning the problem, we look for numbers. Numbers are clues for us to go off of. So 400 feet. Well, what does that mean? That means if I add the lengths here, they would add up to 400. Now, how much fence do I have? Well, I have a Y, an X, and then over here is another Y. So the length of fence would be X plus 2Y. Now that has to be 400. That's how much fencing I have. Equals 400. So this gives us a relationship between X and Y. It says, hey, they're connected. Now what we can do is we can use our relationship to reduce our number of variables. So for instance, I think it's easier to solve for X. So we get X is 400 minus 2Y. And now what we can do is we can take this expression and plug it in. So I say, area now becomes our 400 minus 2Y times Y. Or if you like, 400Y minus 2Y squared. All right. Now we're down to a single variable. Okay. And by the way, does it matter whether we get down to the variable x or we get down to the variable y? And the answer is it doesn't matter. The important thing is we get down to one variable, and then we can use our tools. Whatever we end up solving for, we can then figure out what the other one needs to be. All right, well, let's see. Now, one variable, we're ready to go. Calculus comes into play. We're looking for critical points. So we're going to take our derivative. So we'll think of this here as our function y. So I'm going to write this as area as a function of y. So a of y. So a prime of y is 400 minus 4y. All right, well, that's a really nice function, never undefined. And that should be equal to 0. All right, well, that's not so hard. That says 400 equals 4y, or if you like, y should equal 100. All right, there we go. Now, what is it we're looking for? Are we looking for our dimensions? Because if we were, now we have one of our dimensions. We know that this y should be 100. And of course, if we want x, 400 minus 2y would be 200. So that would be 100 by 200. But is that what we're looking for? And the answer is no. It didn't say find the best dimensions. It just says find the maximum area. All right, so we can take our answer now, namely this y equals 100. We say we think this is where the maximum should occur, and we can plug it back into our original function for area. So we could say the area, when we have y is 100, would be 400 times 100 minus 2 times 100 squared. Now the nice thing is whenever you have hundreds involved, it's easy to do the multiplication because you just keep adding zeros. So the first term would be 4 with 4 zeros. And the second term would be 2 with 4 zeros. And we end up with 20,000. All right, 20,000. Now, if we wanted units, we know we're measuring distances in feet. So we could say 20,000 square feet. Okay, and that's the answer. Now, what haven't we done? Well, let's talk about two things really quickly. One thing is, do we know that this is really a maximum? And how can we figure that out? Well, we can do that really quickly by using, for example, the second derivative test. If we look at a double prime, what do we see? A double prime of y is -4, which is always negative, which means that any point I find that's a critical point has to be a max. So that's good. Now, the other thing we didn't talk about is what about the boundary? Because there are limitations. Y can't be anything. For example, I can't have y be a negative because you can't have negative amounts of fencing. So there is sort of an implicit boundary that comes into play. Oftentimes we don't need that, but it's good to know that we can get it if we want it. So in our case, what would we say? Well, our boundary would say y can be at the smallest would be 0. Now, if y was 0, that would just say put 400 feet of fencing all along the river, and you don't enclose any area at all. What's the largest y could be? Well, it would be if I went straight up and straight down, so 200. So in some problems, we would want to pay attention to the boundary if we think the boundary might have a max or a min. It's not clear from context, but given that we see, definitely it's a max, then we're good to go. All right, well, good. Nice warm-up problem. Let's do some more. So, our next problem. You're doing a final study session before a quiz. It's important to study. The longer that you study, the more you will know, but you will also be more tired. See, this gets into the trade-off. It's like, well, I'll know more, but I'll be more tired, so I won't be able to perform as well. Or I'll be less tired, but I'll know less. So it's finding that nice balance that we're after. After some thought, you come to the conclusion that if you study for h hours, your score on the quiz will be the number 11.2 minus 5 over h plus 1 minus 0.8 times h. So we can see that what happens? Well, the more that you study, that will cause this number to get smaller and this number to get larger. So essentially, what happens here, if you can think about what the effects are. So this effect is I'm going to know more if I study more. I'll know less if I study less. This effect is I'm going to be tired if I study more, and I'll be less tired if I study less. And so we say, aha, each one of these has an effect on my overall score. So let's find that nice balance. How many hours should you study for the quiz, and what will be your score? So now we say, all right, well, this is actually pretty straightforward. They've done the hard part for us. So in some sense, this is like great. We love optimization problems where we get to skip the first step, and that is the finding the formula. So what we should do is we should give this a name. So capital H is our variable. And yeah, it's okay to use capital letters as variables, no problem. We'll go ahead and give this function a name. We'll call it Q for quiz. So our quiz score as a function of H. It's kind of remarkable that we're able to figure that information out. Interesting. All right, anyways, back to our problem. So what do we want to do? Well, we want to take our derivative. Now, it might be useful for us, if we're going to take our derivative, to rewrite this in a more calculusly friendly way. What do I mean? Well, this h plus 1 in the denominator, it's a little bit friendlier for us if we write this as h plus 1 to the negative 1 power. All right, so there we go. Now we're ready for our derivatives. So q prime of h would be what? Well, it would be 11.2. Then the minus comes down, plus 5. Oops, The 11.2 is going to go away because we took a derivative. Okay, so 5h plus 1 to the minus 2 and minus 0.8. All right, good. Now, is this ever undefined? Well, if we think about what the function is saying, this is saying 5 over h plus 1 squared minus 0.8. Now, it would be undefined at negative 1. However, is it possible for us to study for negative 1 hours? So somehow it says, well, we've got to unlearn what we've done. Well, I don't know, maybe watching too many reruns might have that effect, but we're going to assume that, no, we can't study for a negative amount of hours, so it's not going to be undefined. Naturally built into this is that there's sort of an assumption that h is going to be positive. We're not going to say that h could be unbounded by some time. We might say, well, h could be arbitrarily large. Hopefully we're not going to be studying for a quiz for, decades, but all right, we're going to pretend like h can be arbitrarily large. All right, now back into it. So we need to be looking for where the derivative is 0. So let's do that. Now, this would say what? Well, I would say 5 over h plus 1 squared would have to be equal to 0.8, which is another way of saying 8/10 or 4/5. So we can rearrange. So what do I mean? I'm going to multiply the h plus 1 squared over across. Then I'm going to move the 4/5 across by turning it into a 5/4. So that would be 25/4 equal to h plus 1 quantity squared. All right, now we're almost there. You see, what's our real goal here? Our real goal is to get h by itself. So we're just sort of slowly chipping away and peeling off layer after layer. Okay, take a square root. Now, we're not going to do this without pausing for a second and saying, hey, could I have a negative? Right? Because whenever we do a square root, there's sort of the two possibilities, plus minus. And so we always have to say, is there a reason why we're only keeping one of them, and why are we doing that? Well, in our case, there is a reason we're only going to keep the plus, because if we had h plus 1 equals negative 5/2, we'd be back into h being negative, which is out. So h plus 1 equals 5/2. All right, well, we're almost there. Subtract 1, and what do you get? That says h should be equal to 3/2. Okay, good. So that's our critical point. And there we go. Now, is this a max? Is it a min? Well, how do we figure that out? Well, we can do that. It's not so bad. Suppose we do a second derivative test. And the reason I say second derivative test is it's a pretty easy second derivative, because notice what happens. This minus 2 comes down, so you get minus 10 h plus 1 to the minus 3. And if you plug in 3/2, you can see this h plus 1 to the minus 3 is going to be a positive, and there's a negative. So it is a max. So woohoo, good. We got our best score, not our worst score on the quiz. It's always nice to try to get the best score that you can on the quiz. All right, now we're ready to sort of almost get our final answer. At least we have part of it, right? So there's a question. How many hours should you study? Well, 3/2. Or we should study for 1.5 hours. 90 minutes. That sounds pretty reasonable. Okay, what's going to be our score? Well, let's plug in our value here. Q of 3/2. So that would be what? 11.2 minus 5. Now downstairs it'd be h plus 1. Well, that's 5/2. So 5/2 minus 0.8, which we can already write that as 4/5, times 5/2. And what do we see? Well, we see a lot of 5s canceling. That 5 cancels with that 5. That 5 cancels with that 5. And, well, what do we end up with? We get an 11.2. Here, 1/2 would be minus 2. Here, minus 4/2 is minus 2, which gets us to a score of 7.2. All right, that's not bad. That's not bad at all. All right, decent. Good. Passing grade. That's what we want. All right, now we know. Study for at least 1.5 hours for every quiz. Well, you should always study the right amount. Always study the right amount. Hey guys, I can't believe it. Another mistake. And let me show you what I did. And I think you probably saw it. You see, I was so excited about this h plus 1 being 5/2. I put 5/2 there. But that shouldn't be 5/2. That should be h, not h plus 1. So this really should have been 3/2. So this part should have been 4/5 times 3/2. Now, if you work this out, what do you get? Well, that's 12/10. So this should really be not minus 2, but minus 1.2, which means our answer is even better now. See, if you take 11.2, subtract 1.2, that's 10. Subtract 2 more, that means our answer is 8. Good. We're getting better. We're going uphill. Well, be careful. No matter how long you do this, you always can make small mistakes. And so you just want to take your time and don't rush. And if you do make mistakes, don't feel so bad. You know you're in good company. All right. Well, let's keep going. Hopefully, better things ahead. Now, on to another problem. This one has some good applications. Analysis of your past parties has led to the development of a chip index, N squared P. All right, well, what is that? Well, N is the number of nacho chip bags that you have, and P is the number of potato chip bags that you have. So you want to have a good mix, and you want to really have the appropriate amount of each. Now, we have $18 for our chip fund, and every bag of nacho chips costs $3, and every bag of potato chips costs $1. Okay, so how many bags of each chip should you buy to maximize the chip index and thus have a most awesome party? Well, good. We do want to have a good party. All right, so how do we proceed? Well, we really know what we're doing. We know what we're trying to optimize, right? Because it says it here, maximize the chip index. So our goal is we want to maximize our function here would be N squared P. All right, so far so good. There's a catch. 2 variables here, N and P. So we got to get down to 1 variable. But we also saw there were lots of numbers being thrown around. So we suspect the numbers are going to come into play in answering our question. So we said, okay, we have an $18 budget. The nacho chips cost $3 and the potato chips cost $1. So what we're going to do is we're going to use that information to extract our various relationships. So let's see what we have. So $18, well, it's $3 for every bag of nacho chips, so that's 3 times N, and $1 for every bag of potato chips, so that's 1 times P. So now we have a relationship. We can't buy infinite amounts of nachos and infinite amount of potato chips. See, that's the thing with optimization is we don't have unlimited resources. We have to say, okay, given the resources that we have, what's the best outcome? And so we're looking for that sweet balance. And so we're like, okay, well, our best outcome, we got to figure out how do we connect these together. So from here we say, all right, well, let's solve for one of our variables. Now, we can solve for either one, but I would say it's probably best to solve for P, because then we don't have to do any fractions. And I like to minimize the amount of fractions in my life. That's just a personal weakness of mine. If you like fractions, good for you. You're a beautiful person and much more kind-hearted than I am. Go for it. It won't matter. At the end, we'll get the right answer either way. Okay, so we're going to take this quantity here and substitute in for P and see what we get. So now we can say, aha, our function we're trying to optimize is really n squared times 18 minus 3n, or multiplying that out is 18n squared minus 3n cubed. All right, now we're down to one variable. Okay, so that's our function of n. So we can call this, if we want, this is our function of n. Now we're ready to take our derivatives, f prime of n. Well, what do we have? 36n and minus 9n squared. All right, well, never undefined. Well, what else can we say? We can factor out a minus 9n. The reason I make it a minus is I want the highest power to have a coefficient that's positive. So the highest power is the square. All right, so that would leave us with an n and minus 4. Minus 4 because minus 4 times minus 9 is plus 36. So it seems we have two candidates. Well, one candidate is to say n equals 0. The other candidate would be n equals 4. Now, one of these is probably not the right answer. Now, which one can we rule out? And, well, I think you know where we're going. A party without nachos? Are you kidding me? Yeah, that'd be a terrible party. See, if we had n equals 0, what would our chip index be? It'd be 0. Terrible, terrible. So yeah, we have to have some nachos at our party. Okay, so we can rule out n equals 0, which means we're down to n equals 4. All right, well, oftentimes if there's only one answer, that's our answer. So we can say, all right, we need 4 bags of nachos. Good, because remember, what are we looking for? Our answer is how many bags of each chip should we get? So we need to say, what are the bags? How many of each bag do we need? So 4 bags of nachos. This is nacho cheese. Now, how about P? Well, come over here. We take 18 subtract 3 times 4. 18 subtract 12 would give us 6 bags of potato chips. All right, and now we found the right mixture for our optimal party. All right, now we didn't test to see whether or not it was a max or min. A lot of problems won't ask you to do it, but it's good to be able to know how to do it. So how would we do it here? Well, we can do first derivative test or second derivative test. Both work. Here, the derivatives are so easy that I'm partial to second derivative test. When the derivatives get harder, I'm partial to first derivative tests. So I always ask myself, what's easier? Taking another derivative and plugging in at one point, or just sticking with what I have and plugging in at multiple points? And here I think it's, because it's a polynomial, it's so easy to just take another derivative. That's why I'm partial to second derivative here. If you like first derivative, that's great. Both tests will work. What is our second derivative? It's 36 minus 18 times n. And we see that if we plug in 4, we'll get 36 minus, and 18 times 4, of course, is, as we all know, 72. And that's a negative value. So yeah, so this is a max. Good, good. So that shows that we really have found our best mixture to get a good party. It's nice to see that math has real-world applications, because boy, if this doesn't convince you that it's important to study math, well, we'll have a lot more chances. Okay, good. More problems, right? So our next problem. Okay, a rectangular storage container with an open top. So the box needs 4 sides and a bottom. So maybe we should get ourselves a bit of a picture going here. So rectangular storage, well, that's good. In other words, it looks like a typical box. And so here we go. 4 sides and a bottom, but we don't need the top. So we have that, but okay, so there's no top. All right, good. There we go. There's our storage container. All right, and we want this to have a volume of 15 cubic meters. Okay, so that is not an optimization thing. That's a constraint or a relationship, because we're not changing our volume is fixed. So we'll make a little note here. The volume should be 15. That's going to help us. The length of its base is 3 times the width. Okay, well, let's label things. So let's label things as length, width, height. So we're told the length of its base, L, is equal, we should be writing this down, L equals 3 times the width, W. So that's, this sentence translates into that formula. See, we're doing it. We're doing our translation from language into math. It's a beautiful translation. Okay, what else do we have? Well, the material for the base costs $5 per square meter, and the material for the side costs $6 per square meter. In other words, the bottom is a little bit cheaper, maybe because we don't have to print something on the bottom. So we should make some notes about our various costs here. All right, so our cost for the base, so cost for the base is $5 per meter squared. And then we can say our cost for our side is $6. Oh, I should put a dollar symbol here, per meter squared. Okay. All right. Now, find the total cost of materials for the cheapest container. Now, how do we know this is an optimization problem? Well, we see the est. And whenever you see an est, that means there's an optimization. What is it we're trying to optimize? Well, we want the cheapest, which means we're trying to optimize cost. So now we have an idea of what we're trying to do. Our goal is optimize the cost. Okay, so which means our next steps, we need to find a formula for the cost. Now let's think about what's true. Well, we have a couple of things. Let's start with just basic cost at the beginning. So our cost, I'll write that as a cost function C. Well, let's go through our sides. There's the bottom side, and that has area length times width, and the cost is $5 per meter squared, so that would be 5 length width. So this is, if you like, the bottom or the base. Now, here's another side of the box. And this has area width times height. Okay, and what's the cost? $6 plus 6 width times height. But notice there's also opposite, there's another side which has same area, same cost, 6 width times height. And then, of course, there's this front face. Well, that would have 6 length times height. And, of course, the back face is, again, 6 length times height. Notice that this one does not have an opposite side because it's an open top. So there's not, there's a bottom, yes, but there's no top. So I don't have the opposite side. So these are the sides. Good. Good. Now, what we want to do is go through and reduce our number of variables. Right now we have length, width, height. That's 3. We need to get to 1. 1 is our goal. So we say, okay, well, some of them are pretty easy to spot. We know length is 3 times width. Okay, so everywhere where I see a length, I can replace it by 3 times width. So let's do that. So here I would have 5 times 3 width times width, which would make it 15w squared. Here I'd have 12wh, nothing to replace. And then here I'd have 12lh, but remember, L is 3 width. So 12 times 3 would make it 36 times wh. Well, okay, well, hey, that says, what do we really have? 15w squared plus 48wh. All right, that's good. We've gone down to 2, but we still need to get down to 1. And we haven't done anything with volume yet. Well, what is volume? Volume is length times width times height. Now, I know length is 3 times width, so that would say volume is 3w squared h. So, what can that do? Well, what we can do is, for instance, this allows us to conclude that I'll solve for h because, h is just a single h, whereas w is a w squared. I don't want to get square roots involved, so let's solve for h. So if we solve for h, we divide by 3, divide by w squared. We can say that h is equal to 5 over w squared. We say, okay, well, hey, let's replace the h here. Now, we could have been a little bit savvy, and we could have actually solved for w times h and said, oh, that's 5 over w. But that would require foresight, which means we've done the problem before. So, but that seems like cheating if we've done it before. All right, anyways, back to our regularly scheduled problem. Okay, 48 times 5 is, that's right, 240. Good. Aha. And the w over w squared would be 240 over w. Or we can write that as 15w squared plus 240 w to the minus 1. All right, so we've reduced. We've gone down to the point where we have one variable. Okay, so this right here, we can think of this as now, this is our cost as a function of w. All right. Well, what's next? The next thing for us to do is take a derivative. Okay, we've gone down to a function of a single variable. Now we use our function of single variable tools. So we can say c prime of w would be equal to 30 times w, then the minus 1, minus 240, and then it'd be w to the minus 2. Or if you like, 30w minus 240 over w squared. Now you might say, is this ever undefined? Well, it is if we were at 0. Now, what would a box look like if our width was 0? Well, our length would have to be 0, so our height, well, would have to be almost like infinitely tall. So it would be this really ridiculous box. It'd be like a little tiny thing here, and then just going up for a very long time, and then somewhere up very high would be the top of that box. So that would be a very terrible box to build. Not productive at all. Okay, so 0, we say, look, we don't need to worry about that. Yes, that is a place where the derivative is undefined, but that's not going to be a solution. We can't have 0 width. All right, so, well, now we can say, Where is it 0? Where's the derivative equal to 0? All right. Is that equal to 0? All right. Well, let's see. That gets us to, moving things around, 30 times w equals 240 over w squared. Well, multiply. We can get w cubed, because w times w squared, and then 240 divided by 30 is 8. All right, w cubed is 8. Well, we're getting close. That says what should w be? Well, that says w should equal 2. All right, so that should be our point. And we could, of course, take another derivative and check. Does w equal 2 give us a max? Well, I guess we should. It's practice, right? We should do practice. And I don't think I'll do it for every problem, but since we're starting out, we should do a little bit. Again, I think this is one where the second derivative is probably pretty quick. So if I take c double prime of w, I'll get 30 minus 480 w to negative 3. And if you plug in 2, well, you get 30. And here, this w to the minus 3 is an eighth. So it'll be an eighth times 480 is 60. 30 minus 60 is negative. And so lo and behold, c double prime of 2 is negative. So, well, is that good? Makes me nervous here. Find the total cost. We don't want it to be negative. That would be saying we found our most expensive cost. Hold on a second. Hold on. We need to slow down, Steve. Slow down. Aha! I see my mistake. Do you see my mistake? Of course. When I took my derivative, I brought the 2 down, but what did I forget to bring down? I forgot to bring down the negative. Classic rookie mistake. Okay, so it's 30 plus 480w minus 3, which means our c double prime of 2 is positive. All right. Phew. Good. Why did we want our c double prime of 2 to be positive? Because we're looking for the cheapest. In other words, we want a min. All right, so this is truly a min. Good. All right, crisis averted. Back to our problem. Well, we know we found the right length for our width. We know it's at the min. We found the one that makes it the cheapest. What do we do now? Well, the question is, what is our answer? Our answer should be find the total cost. So we're not looking for dimensions, we're looking for cost. So our answer should be a cost. Okay, so what we do is we're going to take this 2 here and we're going to plug it into our cost function. And whatever comes out, that's going to be our cheapest cost. So we're going to get our final answer would be our cost at 2, which would be 15 times 2 squared. 15 times 4 is 60. Plus 240 times w to the minus 1. Well, that's 240 times a half. So that's going to be 120. All right, 60 plus 120 gets us to 180. So that is how much it's going to cost to make ourselves a box, which has a volume of 15 meters. The length is 3 times the width. There's no top. And it says cheap as possible. All right. Well, is that reasonable? Well, certainly it's a positive number. If we'd gone a negative number, we should be really paranoid. But yeah, I think it's a reasonable answer. And that's always a good sign when you get something that's a reasonable answer. All right, good. Well, good problem. There's lots of these problems that they have where it's like make a box or cut corners out of a rectangle. They're all very similar. Lots of fun. All right. So, our next problem. You have just attached a 4-foot-tall TV to your wall, with the bottom of the TV 7 feet above the floor. When sitting on your couch, your eyes are 3 feet above the floor. Okay, so they even provided a picture here, right? So here's us sitting on the couch. We're looking up. Here's our TV, 4 feet, and the TV is 7 feet above the floor. Now you're probably thinking, this is unrealistic. I can afford a place with walls? Okay, don't worry. Someday you will. You'll be able to afford walls. Probably you already have a good TV. Hopefully, well, whatever. Okay. Now, where are we? How far back from the wall should the couch be placed, x? Oh, they've already given us variable names. In order to maximize the angle theta from the top of the screen to the bottom in your field of view. Include units in your final answer. You do not need to verify that your answer is a maximum using a first or second derivative test. Oh, that's nice. We can skip that part. Cool. And there's even a hint. Well, our goal is we want to maximize our angle theta, so we're trying to pick. So you can imagine, of course, if you stood right next to the wall, your couch, you'd have a very, very teeny tiny angle. So that would be bad. So that's, if x is too small, then your angle is very tiny. Now imagine, of course, you were really, really far away. And so you had a giant space you could sit back. Then if you were very far back, your angle would be super tiny. So very far away is a small angle. Very close is a small angle. So we're trying to say, well, where's that sweet spot where this angle is as big as possible? For instance, some people, when they go to a movie theater, they sort of say, well, I want to make sure I get to see as much of the screen as possible. So they'll sort of move around and find their sweet spot where that angle is as big as possible to make it very immersive. Okay, well, what do we do? Well, probably we should see what the hint says. Express theta as a difference of two angles. And there's also another hint. And can you see what they did? They put a little bit of dots here. Well, what is that? Well, the dots are a way of saying, hey, don't worry about the 3 feet. Imagine that you are on the ground. So you put your face down on the ground, and then instead of being 7 feet from the ground, you can say, hey, this space right here is really 4 feet up. And now this is putting us in a good situation because we can say, aha, lo and behold, I'm really starting to see one of my favorite things, which is triangles. Triangles are really nice, especially when we have angles involved. Now, let's follow our hint. So I'm after this angle, and I can see that I can start with a big angle, and then I can subtract off a smaller angle. So if we call our big angle alpha and our smaller angle beta, what can we say? Well, let's look at our big angle first. I have my angle in the corner. I know the opposite side from that angle is 8 feet. The adjacent side is x. So I have an angle, an opposite, and an adjacent. The things that connect all those together is tangent. So tangent of my angle, so tangent of alpha, would equal the opposite, 8, over the adjacent, x. Okay, well, good. Now, for the smaller angle, beta, it's again, I have the angle. I know the opposite side is 4, adjacent side is x. So tangent of beta would be equal to 4 over x. Now, we don't want tangent of alpha and tangent of beta. We want alpha and beta. So how do we get rid of the tangent? In other words, how do we bring them outside? Well, we undo tangent, or if you like, the inverse of tangent, known as arctangent. So we can say alpha is the arctangent of 8 over x, and here we could say beta is the arctangent of 4 over x. All right, well, good. Now, what is theta? Well, theta is equal to alpha subtract beta, big angle minus small angle, which is equal to arctangent of 8 over x minus arctangent of 4 over x. All right. Wow, good. We're doing great. Now, we have our function theta. Really, I can think of it as theta being a function of x, because it only depends on one thing now. Once I have x, I know what's going to happen to theta. Okay, so next step, take a derivative. So here we go, theta prime. So theta prime of x. So derivative of arctangent would be 1 over 1 plus whatever's on the inside squared. Then we have to multiply by the derivative of the inside. Now, the derivative of 8 over x will be what? Well, it will be negative 8 over x squared. If you can't do that in your head, here's how you think of it. So, little note over here, 8 over x is really 8x to the minus 1. So when you take a derivative, what will happen? The negative 1 comes down, that's where the negative is. X to the minus 2, that's where the x squared comes from. All right, so then minus, and again, another arctangent, so 1 over 1 plus 4 over x squared, and again, similar, you get minus 4 over x squared is the derivative of the inside. Okay, well, let's clean this up. Really, a lot of math is just cleaning things up and simplifying our expression, which is why our teachers a long time ago said, simplify, simplify, simplify. It's really important. It's going to help you in the long run. And now that we're doing so much simplifying, we're like, oh, they were right. It is helping us in the long run. Okay, so notice what we do here. 8 over x, quantity squared, 64 over x squared. And then here we'll have minus, and here we'll have 1, or 1 plus 16 over x squared times negative 4 over x squared. I'll go ahead and put the negative 4 in parentheses and negative 8 just so I don't accidentally think that it's a subtraction. Make sure it's a multiplication. One nice thing happens. You see, I can multiply the x squared in the denominator, and if you do that, you see that the x squared over x squared will actually cancel out. So we have negative 8 on the top, and then you'll get x squared plus 64. And then here, minus a minus makes a plus, a 4, and downstairs you'll get x squared plus 16. All right, now, good. So, never undefined, at least now that we have it in this form. So the next thing to do is, when is it 0? That's our critical point, right? If it's not undefined, it needs to look at the case, when is it 0? Well, for that, common denominator will help. So, we'll have negative 8 times x squared plus 16, and then plus 4 times x squared plus 64, and that's all divided by x squared plus 64 times x squared plus 16. Now, at this point, we're going to focus our attention on just the numerator. The denominator is not going to give us anything because it's not 0, and it can't cause the function to be 0. So, focusing on the numerator for a second, so just this part, well, we have minus 8 times x squared plus 4 times x squared, which would give us minus 4x squared. Okay, right, minus 8x squared plus 4x squared. Then minus 8 times 16. Well, okay, what is that? It's a negative 128, right? Yeah. Okay, then 4 times 64 is what? 256. Well, you're probably wondering, how do you know all these? It's powers of 2, right? You know, it's a fun thing when you're walking around to think of powers of 2. 2, 4, 8, 16, 32, 64, 128, 256, 1024, 2048, 4096, 8192, 16,384, 32,768. It's fun to do powers of 2. And if you notice, these are all powers of 2. So it's not so hard to do once you get the hang of it. So anyways, so we have minus 128 plus 256. Well, that combines to give us a plus 128. And we're saying that equal to 0. Okay, so if you move the 4x squared across, divide by 4, well, 128 divided by 4, would be what? Well, it would be 32. All right, so now we have what x squared equals. So x squared should be 32. Okay, so if x squared should be 32, what should x equal? And the answer is x should equal the square root of 32. Now, it did say include units, and what is it we're looking for? Well, we're looking for how far back should we be. So we're really looking for x. Our goal was to find x, not to find theta. So since everything here was measured in feet, this says x should be square root of 32 feet. And that will be our answer. We don't need to justify it being a max or min because they said we don't have to. So, woohoo! Nice. All right. Wow, what an interesting problem. And now, how far is square root of 32? You might be wondering. Well, it's around 5.5. You see, 5 squared would be 25, 6 squared would be 36, and 32 is in between. So 5.5 feet. That's not very far back, but, well, you may not live in a very big space, so you make do with what you can. All right, good, good. Well, another problem, right? On to the next one. So, you are designing a container which contains of, typo, not contains of, consists of. I am so sorry about that. Consists of a cylinder with no top. Oh, so this is kind of similar to the one we did before, right? So now what we have is instead of a box, we just have a nice little cylinder. Okay, there we go. So there's our cylinder. So we have a base down here. There is a base down here, but there's no top. So we'll make a little note to ourselves. No top. Good. Now, the material to construct the bottom cost thrice as much as the material to construct the side. Okay, thrice, by the way, is a very fancy way of saying 3 times. So thrice equals 3 times. It's sort of like twice, but instead of it's thrice. Okay, all right. The cylinder must have a volume of 192 pi cubic inches. So we know our volume needs to equal 192 pi. Determine the radius and height of the least expensive cylinder given these constraints. It's a little bit different here. So we weren't after, well, beforehand, what did we do? If you remember the problem we did a few back, we were saying, well, what's the cost? Now our answer is, what are the dimensions? So make sure you're paying attention because it can ask for different things for the output. All right, well, where do we begin? The best place to begin would be, let's write down some various things. So first off, we know we're after a radius and a height. So we should put that into our picture. Well, height of the cylinder, and then down here would be our radius of our cylinder. We'll use R and H for radius and height. What's the volume of a cylinder? Well, a volume, you can imagine, you start with the circle, which would be pi r squared, and that gives you the area of the base. Then you take the area of the base times the height. So the volume of a cylinder is pi r squared h. And we know we want 192 pi to be our volume. All right, so there we go. There's our volume. Now, well, it's not our volume, it's our constraint. So that gives us a relationship between R and H. What else do we want? Well, we have information about the cost, right? The material to construct the bottom costs thrice as much as the material to construct the sides. So let's talk about our cost. So our cost function is what? Well, our bottom, the area is pi r squared. Okay, so pi r squared, this is the area of our bottom. All right. And now, how much area is on the side? Well, to figure that out, one thing you can do is you can reach into your pocket and pull out your scissors, and you cut along the side, and then you would take it and you'd lay it flat. So if you were to lay this flat like a rectangle on the sides, what you would see is you'd say, oh, there's the height, h, and this bottom here forms the rim, the outer edge of that circle, also known as the circumference. And the circumference of a circle is 2 pi times the radius. So we can say, all right, the area of the sides is 2 pi RH. Now, we have to have material for both the bottom and for the sides. Now we talk about the cost. We're not told the number for either amount, and so we just make up a number for one of them and figure out the other. The thing that you might say, well, wait a second, what if we guessed the wrong number? It won't matter because we're going to be scaling everything. And since everything scales together, the result will be the same. So we pick a convenient number. So here we are told that the bottom costs thrice as much as the sides. So let's make the sides cost 1, and then the bottom would cost 3 times as much. And so our cost, we can say, well, it's 3 pi r squared plus 2 pi rh somethings, where somethings are some unit to be determined. We may never know. That's all right. Okay, so there's our cost function, but we needed to get it down to one variable. So that's where our volume comes into play. I can use the volume to solve for one of the variables. So for instance, I could solve for height. Get rid of the pi's. We can say height is 192. Divide that by r squared. So now plug that in to the single h. Okay, so we can say now our cost function as a function of just r, because we're going to replace the h, is 3 pi r squared plus 2 pi r 192 over r squared. Or if you like, that's 3 pi r squared, and 2 times 192 is 384, so plus 384 pi, divide that by r, because there's an r over r squared. So now we have our cost function down to one variable, so we're ready to take a derivative. Taking the derivative, we get the derivative of cost. Well, 6 pi r, and then here, this is like a 1 over r, or if you like, r to the minus 1. So that would be minus 384 pi over r squared. All right, good. Now, r equals 0 is a problem with this derivative, but we would not choose r equals 0 because if r were 0, for example, we could never get to a volume of 192 pi. It would really mean that we'd have this sort of infinitely tiny cylinder as far as the base goes, but infinitely tall. Terrible cylinder, terrible cylinder. Okay, so we'll set this equal to 0. Well, what does that say? It tells us that 6 pi r is equal to 384 pi over r squared. Now, some good things happen. We can get rid of our pi's, which is nice. Woohoo! Good. Now, what else can we do? Well, multiply r squared to both sides gets us to r cubed equals, and divide both sides by 6. Well, does 384 divide into 6? One would hope, and it does. It's 64. Now, one way you can see is 384 is close to 360. 360 is 60 times 6, but there's 24 more, and so I need 6 times 4 to get to the 24. That's where the 64 comes from. And they gave us a nice number to work with. They're so kind. All right, so if r cubed is 64, that tells us that r is 4, because 64 turns out to be 4 cubed. Woohoo! Good. Nice, clean numbers. Nice, clean numbers. All right, now, we now know what r is, so that's one of our dimensions. Okay, how did we get h? Well, to get h, we're going to take this information about r here, and we're going to go all the way back to there. And that tells us what h is in terms of r. So we get that h is 192. Divide that by 16. Now does 192, is that divisible by 16? And if it is, then that means that they really were careful in making this work. Well, I think they were really careful. You can see, if I multiply 16 times 10, that would be 160, which leaves me with 32 to go. That's 16 times 2. So 192 divided by 16 is 12. Ah, good. So our final answer, we can say that our radius should be 4, and 4 what? 4 inches, because we're measuring things in inches, and our height should be 12 inches. And there we go. Good. Nice. Nice clean answer. All right. Well, on to another problem. Okay. I think this might be our last one for now. So, for a greater than or equal to 0, find the point on the curve y equals square root of x closest to the point a comma 0. So let's think about what the picture is. So we have the curve y equals square root of x. Now, that looks something like the square root curve. It kind of looks like half a parabola if you turn the parabola on its side. So here is our curve, y equals the square root of x. All right. Now, what do we have? Well, we have a point. A comma 0 means we are on a point on the x-axis. So we're down here. So here is at x equals a. And now I'm thinking about, there's lots of points here along y equals square root of x. And among all of them, we're looking for the one where the distance is as small as possible. That's our goal. Where is the distance as small as possible? All right, good. Now, how do we know this is an optimization problem? Of course, we should learn to recognize optimization problems. And of course, here we see it. It's the est. All right, so what is it trying to optimize? Well, it says here, close est. So that's why we're talking about distance. It's all about optimizing distance. So we need to come up with a formula for the distance. Now, distance from where? Well, here's one point. This is our point a comma 0. And now I'm going to say, well, there's another point over here on the curve. So what does this look like? It looks like x comma square root of x. Because I have that on the curve, y equals square root of x. So I want to pick the value for x, which makes this distance here as small as possible. So let's write down our formula for distance. So we have the distance between 2 points would be equal to the square root, and then we subtract the x values and square it, x minus a squared, and then we subtract the y values and square that, plus square root of x minus 0 squared. Well, what can we do? Well, we can do a couple of things. Square root of x quantity squared will get us back to what? It'll get us back to x. All right, that's good. Now let's pause for a second and let's just say, what do we like, what don't we like? Well, we like that we have an expression of one variable. That's great. That's really what our goal is. Get to a function of one variable and then we can optimize. But I think there's something that we don't like going on, and that is the square root. Wouldn't it be great if we could get rid of the square root? And if we can get rid of the square root, how do we do it? Well, it turns out there is a way to get rid of the square root, so that it makes the problem easier to do. And the way that you get rid of the square root is you just don't bother with it. So, in other words, I haven't actually said what function I'm going to optimize, because I'm allowed to say, well, what is it I'm trying to optimize? So I'm not going to optimize the square root. What I'm going to optimize is what's on the inside of the square root. Okay, so let's take a moment here to pause and say, why can I don't want to use the phrase get away with this, but why can't I get away with this? What allows me to say, hey, you just have to focus on the inside? Well, it turns out that the square root function has a really beautiful property. And very conveniently for us, we can actually point to a square root. See, this is the square root function. If you remember when we talked about functions being increasing, decreasing, there was a phrase, monotonic. And so the square root function is an example of a monotonic function because it's always going up. Now, whenever I have a monotonic function, if I want to optimize something where I'm plugging it into a monotonic function, I say, look, I just have to optimize the inside. So if I want the square root of something to be small, I make the something small. If I want to make the square root of something large, I make the something large. So it says, hey, focus on the inside, and that will be enough. That suffices. There is one small thing which is also incredibly important, and if we overlooked it, we might get the wrong answer. We haven't really talked about this in a while. This is a problem which has a boundary built into it. So if you look at this expression, x minus a squared plus x, you say, hey, it looks like any x works. But is that the case? And the answer is no. No, it's not the case. So we're going to look at x minus a squared plus x for x greater than or equal to 0, because I can't plug a negative value in. That wouldn't make any sense. Okay, so now we know what we're doing. We're going to take x minus a squared plus x. We're trying to optimize that, assuming that x is greater than or equal to 0. So, well, let's give this a name. So we'll call this here our function of x that we're working with, f of x. All right, now, what is f prime of x? Well, that's not so bad. It's a polynomial. You can do the chain rule, 2 times x minus a plus x. All right, is this ever undefined? Nope. Beautiful. Okay, so now we'll say when is this equal to 0? Well, that says what? Oops. I took my derivative wrong. Derivative of x is not x. Derivative of x is 1. Oh my, that's why you always double check your work. Okay, so 2x minus 2a plus 1 equals 0. Okay, and then we can move things across. That says 2x is equal to 2a minus 1. And that says, hey, x should be 2a minus 1 over 2. Good, good. Now, that's where the derivative equals 0. Okay, now, do I have a max or a min? Well, that's also easy to spot, because I can take the second derivative. Second derivative is 2, which is positive, which means that's definitely a min. Okay, so that should be our answer. X equals 2a minus 1 over 2. It's always going to be a minimum. Should we be worried? All right, it seems like we're done. Is there any subtlety? I mean, I said there's something here. We got to be careful though, right? We said x has to be greater than or equal to 0. But what if I chose something close to 0? Like, 0.01. What do you see? You get x as a negative value. What is that saying? Well, what it's saying here is you have the following situation. So you have some possibilities. So what happens? There's two possible outcomes. If 2a minus 1 over 2 is greater than or equal to 0, and then we're fine. That's a perfectly valid answer because it's an available option for us to choose. So then we let x equal 2a minus 1 over 2. All right, okay, good. Or, by the way, another way to write this is a minus a half. If 2a minus 1 over 2 is less than 0, well then the picture is we have 0 And then over here is 2a minus 1 over 2. And if you look at the derivative, you can go into the first derivative if you like. You can see that from 2a minus 1 over 2, I'm negative to the left. So our derivative is negative, our derivative is negative. So we're always decreasing our values. Oops, so many mistakes here. Derivative is positive. Derivative is positive. Okay, all right, I'm just a little bit excited here, of course. That must be it, that must be it. So what's happening is I'm increasing every time I move to the right. So 0 is as far to the left as I can go, which means that I should pick x equals 0. So this is a case where the optimum occurs on the boundary. All right, good. So, the optimum is on the boundary. That can happen. All right. So there we go. All right. So yeah, good. So we can actually combine these two answers together and say, well, what is the answer? In general, we can say that you take either, whichever one is larger, the max of a minus a half or 0. And that would be the farthest we can get, the best, most ideal point we can reach. Now, after all of this, I do want to say, and I apologize, I made a couple of mistakes along the way, but we got to the right answer at the end. There is a nice, interesting interpretation here. So what's happening is if I'm far from 0, I do go up to the curve. As I move close to 0, eventually from the point a half on down, I should always go straight to 0 and not up to any point on the curve. Just straight to the origin, 0, 0. There's an interpretation of this if you go back to thinking of it as a parabola. So here's a fun little fact. If you take a normal parabola, y equals x squared. So here's our parabola. You can drop a circle here. And now the question is, what happens to the circle? Well, it turns out that if you have a large circle, it's going to not go all the way down. So on a big circle, it'll get stuck at the sides. If it's too big, it can't reach the bottom. On a really tiny circle, it'll get right to the bottom. And what this shows is that there's sort of a sweet spot for circles. So if your circle is exactly the case where it has radius a half, then that's the largest circle, which when you drop it into the parabola, it will sit exactly touching the bottom. Any smaller, it'll touch the bottom. Any larger, it can't reach the bottom. And so it's a transition between two different possible outcomes. All right, well, I think we should probably pause for now. A lot of practice, and we'll do some more. Important thing is keep practicing, and it's okay if you make mistakes, but look for them and make sure you catch your mistakes before you get too far off. Because the sooner you catch your mistakes, the better. And it's easier to correct your mistakes earlier than it is to correct them later. All right. Well, thank you.